So in many cases, you guys, in many cases, it's not uncommon for this class to actually get easier with each passing exam. And a lot of that is just adjustment. It really is. It's just, you're getting adjusted to new material. You're removing a lot of rust. Every instructor is weird and different. Every instructor has idiosyncrasies. And by this point, you're probably used to that as well. Having said that, having said all of that, yeah, the glass is really half full. It is. You should have confidence in yourself. You're here. All right. So now we have a brand new force called the magnetic force. And this was, if I had to make a list of maybe the 3 YouTube lecture videos that you should watch before lecture, this is probably one of the 3. There's so much going on with chapter 28 in terms of visuals and in terms of just new stuff, and it's very visually rich. There's a lot of 3-dimensional stuff that you have to be aware of, and you had to be aware of 3-dimensional stuff before, but I think that's maybe even more true chapter 28. The other thing that makes chapter 28 perhaps challenging for some but not for others is the fact that very central to a lot of stuff, not everything but a lot of stuff, is the cross product. So this is where I'm a little bit concerned. Cross product is an integral component of chapter 28. The physics class you had before this class, you absolutely should have done a lot with cross product. You should have used cross products for torque analysis, and you should have used cross products for angular momentum. There is no way you should have walked out of your prior physics class without using a lot of cross product stuff within the torque and angular momentum topics. And on top of that, some of you might have done stuff with cross product via your calculus class, but and I can't remember when you learn about cross. I don't know if that's Calc 1, 2, or 3, but it doesn't matter because the physics class you had before this one, you definitely dealt with cross product. And if you haven't, that's not meant to be that's not meant to be ominous. If you haven't, you just have to speak up. I can give you very precise and short and sweet jumpstart resources within Wiley Plus to get you to where you need to be with cross product. It's not insurmountable. It's actually not a big deal. So having said that, we now have an electron moving through a magnetic field. So we actually add to our list. How many forces have we dealt with in physics life? We've dealt with the gravitational force, also known as weight, equals mg. We know about kinetic friction. We know about static friction. We know about the normal force. We know about string tension. We know about the electrostatic force and maybe some other stuff we know centripetal force, F sub c equals mv squared over r. We know about Newton's universal law of gravitation, which says, generically speaking, this equals g m1 m2 all over r12 squared. And now we add the magnetic force. The magnetic force is another force that goes onto this list of forces. The great news is Newton's second law still applies. And the other sort of asterisk you can put next to this is, in our universe, we have 4 fundamental forces. We have the gravitational force. We have the strong force, which has to do with the atom. We have the weak force, which has to do with the atom. And we have the electromagnetic force, which has to do with electricity and magnetism, which for us is basically chapters 21 through 31. 21, 31 are all within the realm of electromagnetism. Okay. So again, this is our new inductee to our list of respected and revered forces, the magnetic force. Here we have an electron moving through a magnetic field. Okay, so here's the electron. There's the electron, and it's moving through a magnetic field that has unit vectors. At a particular instant, the electron has this velocity. So let's draw the velocity. At a particular instant, at this instant, here's my electron's velocity. 2.21 meters per second in the I hat. There's my X velocity. And 4.31 meters per second in the J hat direction. Here's my Y velocity. So I'm going to label this. This is the electron's X component. Vx equals Vx I hat. I hat is the unit vector that's in the plus or minus in the X direction. And with my numbers here, it's 2.22 meters per second I hat. Here's my Y component. Vy, because this is there's two components to this electron. Vy equals just generically Vy times J hat. My Vy is 4.31 meters per second J hat. That's my electron's velocity. And if I need it to carry, maybe I do, but this would be the net. The net velocity of this electron is right here. And I would just say, this is just my net velocity. And I could say, well, my net velocity is just the vector sum. It's Vx I hat plus Vy J hat there. That's what my electron is doing. And at the moment it has this velocity, it's exposed to this magnetic field right here. I'm not going to draw this magnetic field yet because I don't know what this X component is. In fact, I think this X component is my $sign. It is. So I was going to draw this. I will draw the magnetic field, but not just yet because I need to do some work to find it. At a particular instant, the electron has this velocity and it has this force. It has a force acting in the K hat direction. So if I was going to put all of this on a three-dimensional coordinate system, here's the three-dimensional coordinate system. Okay. I'm going to alter this because I didn't mean this to be perfectly lined up. So not to scale, but I'm just altering it because I want this vector to be not where it is. Okay. So there's my electron. Those are my unit vector components. Dealing with unit vectors is so much easier than dealing with vectors that aren't in unit vector form. So it says, here's the magnetic force, 3.98 times 10 to the negative 19th in the K hat. So here's my magnetic force right here. It's in the plus K hat direction. So here's plus K. So this force, this is F, which stands for force. B stands for magnetic. So F subscript B is the magnetic force, which again is a brand new entry, magnetic force. So fundamental force of nature. And for us, this is 3.98 times 10 to the minus 19th newtons in that K hat direction. So I should be able to figure out B subscript X. This is my $sign right now. And here's the starting point. It turns out that this is how nature behaves. Nature behaves the following. Here's how nature behaves. F subscript B equals QV cross B. This is how nature behaves. And again, I'm giving you the 25-cent tour of the $1,000 YouTube video that goes into much more depth and breadth and background and stuff. But for now, I'll just recap it very briefly by saying, apparently, when a charged particle moves through a magnetic field, it feels a force. And the force that's felt by this charged particle depends on the magnitude of the charge and the speed and the strength of the magnetic field. So it depends on the charges. It depends on the particle's charge, velocity, the strength of the magnetic field. And then this is what might be new for some of you. And it depends on the perpendicularity between V and B. This is what cross product is. Cross product is the product of perpendiculars. You use the cross product operation to figure out the product of perpendiculars. I want to basically do this. I want to find the component of velocity that's perpendicular to the magnetic field, or completely equivalently, I want to find the component of the magnetic field that's perpendicular to the velocity and multiply them together. And you know what does this? V cross B, product of perpendiculars. And there's another way I can write this the same way using magnitude angle Q. I'll do this. The magnitude of this magnetic force is going to be the magnitude of QV cross B. And here's another way of saying the exact same thing, QVB sine theta. Sine theta, this sine theta term, this finds the perpendicularity between V and B. Let's just say, a little sidebar. Here's V. Here's B right here. This is my magnetic field vector. This is my velocity vector. All that sine theta is doing, sine theta is saying, hey, I'm going to find this component right here, and this is what's called B perpendicular. And B perpendicular equals B sine theta. It's that simple. It's that simple. Or what if you didn't want to find B perpendicular? What if I wanted to find V perpendicular? And you have to be able to be this flexible or have this insight. I have the same two vectors here, but I could do this. I could just maybe I could extend this vector right here, maybe use a gray line and say, well, here's my B vector right here. And here's an alternative that gives me the exact same result. I could call this projection right here, dot, 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 dot. This right here would be V perpendicular. And V perpendicular also equals V sine theta. So no matter how you set things up, no matter who you give primacy to, velocity or magnetic field, sine theta captures that perpendicular element. So now let's do the cross product. Number three. Okay, I need to do force equals QV cross B. You've done very similar operations with torque analysis and angular momentum analysis, and we're just doing it here now. And again, having said that, I know some of you might be rusty with cross products. Some of you maybe because of whatever the circumstances were when you took your prior physics class, you never got into cross products. And that's not catastrophic. It just means you've got to reach out, and I can tell you right away where to look to get jump started. But here's F sub B. F sub B equals, here's my number, 3.98 times 10 to the minus 19th newtons in the k hat direction equals Q. We're talking about an electron. So I know for an electron, Q equals negative 1.6 times 10 to the minus 19th coulombs. So I guess I'll put that here. Negative 1.6 times 10 to the minus 19th coulombs. And now I got to do V cross B. Here's how I'm going to do V cross B using cross. This is called the method of Saris, or Saris's method. Some of you have learned this method. Some of you learned a different method. You can use whatever method you want. And if you never learned how to do cross product, you should contact me. But here's here's how I'm going to do V cross B, because right now, here's V cross B, I hat, J hat, K hat, I hat. So this is just an operational technique to do cross products. And there's many variations to this. This is just one of many. This is the way I was taught. You were either taught this way or a different way, which is fine. All right. And then this would be VX, VY, VZ. So it's very operational. It's kind of like, I think of this like the mesh method. Every now and then, you guys, we just got to be super operational. VX, VY, VZ, VX, VY, and then this would be BX, BY, BZ, BX. So I'm just, all of this is just setup. This is just generic setup. So there. In step 4, this is my generic setup of the cross product. And what you see here, this is V cross B. So I'm going to do the same thing now, but with numbers. Number 5, 3.98 times 10 to the minus 19th newtons in the K hat direction equals negative 1.6 times 10 to the minus 19th coulombs. That's Q. So, okay, I've got, there's Q is represented, the force is represented, and then here's my V cross B, my same headers, I hat, J hat, K hat, and then you just repeat I hat, J hat, and then VX. My velocity in the X, according to my problem statement, my X velocity is 2.2 meters per second, 2.22. 2.22. I'm not going to write down meters per second. Meters per second is assumed. So there, this is VX. This is VX. Here's VY. VY is sitting right next door. For me, VY is 4.31 J hat. 4.31 J hat. And then K hat apparently is 0. And then I repeat, what's I hat again? Oh yeah, it's 2.22. That's given. And my J hat is 4.31. Done with my velocity. What's my magnetic field? According to my problem statement, this is my magnetic field. Here's the X component of my magnetic field. It's just B sub X. I don't know what it is. That's my $sign. Here's my Y component, 3.39 BX. 3.39 BX. Here's my Z component. There is no Z component. So once again, then you just repeat it. You repeat it. It's just a methodology that was born from just a lot of background math and a lot of just setting things up in a standard way to find out the product of perpendiculars. And this is 3.39 B sub X. Okay, so then in this method, I would do crisscross. So here's criss, 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 criss. So I think of this as crisscross. Crisscross. Crisscross means down to the right. Cross means down to the left. Okay, so question, when I'm executing this matrix, what is I hat times 4.31 times 0? That equals 0. So that just goes away. That equals 0, low-hanging fruit. So then what's my other criss operation? J hat. What is J hat times 0 times B sub X? That answer is also equal to 0. So more low-hanging fruit. My last criss operation, what is K hat times 2.22 times 3.39 BX? It's not equal to 0. It is actually equal to 2.22 times 3.39 B sub X K hat. Okay, done. Done with the criss, 2.22 times 3.39 BX. Now it's time to do the cross operation. Cross means diagonally down to the left, down to the left. So here is that operation. What is k hat times 4.31 times b sub x? It's not equal to 0, and I have to prepend a negative. So I'll add this here. Prepend or negate. Flip the sign. I'll just say prepend a negative. Prepend means tack on at the very start. Okay, so I have to tack on a negative at the very start. We're definitely doing cross product stuff. So this would be, here's my negative sign that I just automatically throw in there. And this would be 4.31 bx k hat. Okay. What is, I'm still doing my cross, I hat times 0 times 3.39 b. That's equal to 0. Low-hanging fruit. And here's some more low-hanging fruit. So what I just did here, I set up the cross product and I executed the cross product using this particular method. In some cases, you could use your calculator. In this case, I don't think this really lends itself to a calculator. But again, this is where I have to assume, and I don't want to assume. I need to assume you have dealt with this through your prior physics class, and it's not a super big deal if you haven't. Okay, so now let's just finish this. Number 6 says, all right, well, everything's a k hat. My fourth, here's a k hat, here's a k hat, and here's a k hat. So here's what I'm left with when all of this smoke settles, because all I'm finding out is now that I've taken V cross B and multiply it by this charge, I end up with 3.98 times 10 to the minus 19th newtons in the k hat equals negative 4.31 bx k hat plus 2.22 times 3.39 bx k hat. That's what I end up with. And you can cancel these k hat vectors as if like they're common terms. K hat's a common term there, a common term. So just solve for bx. Solve for this x component. And when you get this answer, know that this answer just came from product of perpendiculars and doing a very specific cross product operation. Okay. 3.98 times 10 to the minus 19th. Oh, I forgot one thing. I forgot to multiply by charge. Okay, so I'm just going to move this a little bit out of the way over here, because all of this was multiplied by my charge. So square bracket, and this charge was negative 1.6 E minus 19th coulombs. Okay. All right. A new unit, Tesla, brand new unit. And if I did dimensional analysis, apparently newtons equals coulombs meters per second times B. So apparently a Tesla is a Newton second per coulomb meter. More on that later, because I know you're probably doing something else. It's 9:18. And we're back. All right, moving on. Moving on. Chapter 28, quiz 2. There's no cross products here, but a big part of this chapter is our cross products. So just want to keep reinforcing that point. And maybe I'm being a little bit paranoid. Maybe everyone here is very proficient with cross product operations. I'm just concerned. All right. So now we have this quiz, chapter 28, quiz 2, which is a homework problem. They're all homework problems. You know that. Okay, so a charged particle moves into a region of a uniform magnetic field. It goes through a half a circle and then exits. The particle is either a proton or an electron. You must decide which. It spends 114 nanoseconds in this magnetic field region. What's the strength of the magnetic field? Okay, so this is good stuff. No cross products here, but magnetism. Again, chapter 28 is chapter 28. What's the short title of chapter 28? Magnetic forces. Magnetic forces acting on moving charges, which is a huge deal. This is so much of modern society is predicated on magnetic forces acting on moving charges, like motors, for example, motors, solenoids, on and on and on. And just look at motors, electric motors. I mean, that powers just a giant swath of our world, electric motors and solenoids. You find solenoids in robotics, and robots move usually via actuators and solenoids. So anyway, we have a particle. I'm going to draw a particle. Here's my particle that's encountering a magnetic field region. So, and I'm going to draw this particle right here, right at the transition between outside and inside. So my particle right there. There's where my particle enters the magnetic field. And this particle is either a proton or an electron. I don't know which. So it's either E minus for electron or E plus for a proton. It's either a proton or an electron. I can figure out what it is because I have a few bits of information. At the point this particle enters this magnetic field, this is what the velocity vector looks like. It looks like a vector that's tangent to the path. So let's label that. This is the velocity upon entry. This is the entry velocity of this proton or electron, and you can see it's tangent. It's tangent to path. Okay, so this is V for velocity. V for velocity. So I know a few things here. I know the velocity of this particle is V. I know this magnetic field is coming out of the page. So this is, again, a brief recap of a ton of time spent in the lecture videos talking about what it means to be, what this dot means. So this dot means dots. Whenever you see a dot like this, whenever you see a dot, it's a visual representation showing that It's out of page. It's coming out. It's coming out of page towards you. So think of it like an arrow. You know, you here towards your eye, towards your eye. So just think of an arrow. Think of like, here's an arrow. Here's an arrow that somebody shoots. Sounds kind of gruesome. Here's an arrow that somebody shoots towards my eye. Here's my eye. So if I'm looking at this arrow coming straight towards me, I'm going to see it as a dot, just the tip of the arrow. Okay. If on the other hand, I'm looking at the arrow going away from my eyeball, like I'm drawing here. Here's my eyeball looking at the tail feathers. The tail feathers of an arrow, I'm seeing it as just an X. So X means something is coming. I'm sorry. X means something is flowing away from you. A dot means something is flowing towards you. So these dots means everywhere in this shaded region, I have magnetic field lines coming out everywhere. And they're just showing one of them. If I wanted to do this, I could draw a whole bunch of them. Like there's a magnetic field here and here and here. So everywhere I have these magnetic field lines flowing out of this shaded region, perpendicular to the screen, coming out, not going in, but coming out. Okay, so rather than just draw all of these magnetic field lines, which I could, that's a good practice. I'm just drawing one representative. I'm just saying, hey, this one single dot right here, this is signifying that everywhere in this shaded region, there is a magnetic field and it's flowing out of the screen towards your eyeball. So I know Q, V, and B. I know Q, if it's a proton or an electron, Q equals, I'm just going to repeat it. Q equals negative E for an electron. Q equals positive E, fundamental charge, for a proton. So maybe E for electron if you wanted. All this. All right. So I know the charge. I don't know if it's positive or negative, but I know the charge. So here's what I do know. I know Q, I know V, I know B. I know all of that. And from the introductory statements made to chapter 28, it turns out through observation, through experiment and observation, it turns out that this is the relationship. Magnetic force equals QV cross B. That's that cross product representation. Or if I wanted to do magnitude angle, I could just say, well, as far as magnitudes are concerned, the magnitude of that magnetic force is equal to QVB sine theta, where theta, it's always the same. We've seen this before. Theta is the angle between these two vectors. Okay. So I can say one thing here. As long as I'm writing that down, I can just say, aha, theta equals 90 degrees. Everywhere, no matter where this particle is, because apparently this particle enters the region and then the particles at some later time, my particle's right there. And at that later time right there, the velocity of this particle looks like this. It's still tangent. It's still tangent to the path, but it's moved. The velocity vector has shifted direction, tangent, like that. But no matter where I draw this particle, whether it's an electron or a proton, maybe I'll draw it right here. If I draw it right here, at that particular point, the velocity is in this direction, tangent. Okay, no matter where this particle is, the angle between the velocity vector and the magnetic field vector is always 90. So make sure you're satisfied with that, because the magnetic field is always coming out of the screen as shown here, and it's always going to be perpendicular to the velocity vector, no matter where I draw the velocity vector. So that's what I'm saying, theta equals 90. Make sure make sure you're seeing that. Don't just say, okay, if you say so. That would not be optimal. All right. So now I need to find out, is this a proton or an electron? I don't know quite yet. So I'm just going to keep going. Number three. All right. F sub B is the magnetic force acting on this proton or an electron. And you know what this magnetic force is doing? It makes the electron or proton, whichever it is, move in a circle. In this case, a semicircle. I'm just going to leave circle. So it's moving. It would move in a complete circle if the entire region were a magnetic field, but only half the region is. So it starts to move in a circle, but then when it exits the magnetic field, there's no more force making it move in a circle. So you get a semicircle. So the magnetic force makes it move in a circle. And why is that? Because of this relationship, because F equals QV cross B. This is why. It's this cross product right here. This cross product says, hey, no matter what's going on with V and B, F is always perpendicular. F is always perpendicular to the plane formed by V and B. So, okay. What does that mean? All right. It means that here's B. Here's my B vector right here. All right. So that's coming out of the screen. Here's my V vector. I'll just talk about this particular snapshot, right? Point of entry. This is where my particle first enters the magnetic region. So there's V for velocity. There's B for magnetic field. I'm going to get rid of these just to clear the clutter. Okay. So at this point of entry, I know that the force, this is what cross product is telling you. Cross product is saying, hey, F sub B is perpendicular to the plane formed by plane formed by V and B vectors. That's what that's saying. And there's a little shorthand. There's a clever little right-hand rule. I call this flat hand right-hand rule. So here we go with the right-hand rules. Number 4, flat hand right-hand rule to the rescue. Flat hand right-hand rule to the rescue. Okay, so here's the flat hand right-hand rule. You hold your hand like this. So here's your not your left hand, your right hand. You make your right hand flat shape, but then you extend your thumb like this. So it's and my pinky's a little bit out of joint there, but you keep these fingers, you keep your 4 fingers together, and you sort of have your thumb out, trying to get away. Your thumb is movable. So my 4 fingers are glued together, but your thumb is adjustable, and you keep your hand flat. So when you do that, if this is your flat hand, I'm going to try to draw this here. Here's your fingers, all 4 fingers kind of lined up. And then here's your, this is not going to go well. But here, let me just do this abstractly. Let's just say these are your 4 fingers. So Picasso, anyone. Those are your four fingers all kind of stuck together, flat, four fingers. And then your thumb might be coming out like this. Can I rotate that? Maybe I can't rotate that. Your thumb is coming out. I'll do it like this. Here's your thumb. There's your thumb. And here are your four fingers. 1, 2, 3, 4. 4 fingers. 1, 2, 3, 4. And this is little pinky. Okay. Not bad, really. I mean, I can see it, but all right. So these are your four fingers. This is your thumb. Thumb is adjustable. 4 fingers are 4 fingers. And then this whole thing here, your thumb and your 4 fingers, no matter where your thumb is pointing, it's always flat. This is flat. Your thumb and 4 fingers are flat in a plane, in planar. Okay, so that's the whole setup. Here's my 4 fingers. Here's my thumb. Your palm points in the direction of the magnetic force. So when you do that, you know that the direction of your palm is indicating the direction of the magnetic force. This is F subscript B. This is your palm direction. This is your palm, not the back of your hand, but your palm. Your thumb points, your fingers issues. I'll do thumb. Your thumb points in the direction of velocity. So my velocity in this case would be shown by the thumb direction. Okay, so V for velocity. Your fingers, last but not least, show the direction of the magnetic field. So here's the magnetic field. Okay, and this is B. So let me just recap this. B is fingers, direction of 4 fingers, direction of 4 fingers. The direction of your palm. So it'd be exactly like this. Here's my palm. My palm is facing that way, like that. Just that's the direction of my palm. And that's F subscript B. That's my magnetic force. And my thumb, and I can move my thumb, but no matter how I move my thumb, my hand remains flat. So maybe my thumb is kind of close to the 4 fingers. Maybe my thumb is far away from my 4 fingers. Whatever my thumb is doing, it's forming, it's in the same plane as my 4 fingers. All right, so there you have it. This is how you figure out the direction, or this is the flat hand, right hand rule. Most people just call it right hand rule, but I call it flat hand, right hand rule because there's another right hand rule where you don't keep your hand flat. But there it is. These are my key players, V, B, and F. Okay, so if we do this flat hand, right hand rule, all right, so here we go. Flat hand, right hand rule. This is the direction of velocity. So I got that. This is the velocity direction, obviously, but just saying this is my velocity direction. So this is that's my velocity direction, and that's going to be my thumb. Thumb. My thumb points down. My thumb points down, indicating the direction of velocity, because that's what the thumb does. The thumb indicates the direction of the velocity. I'm going to get rid of this because it's getting cluttered. Okay. My fingers are pointing out of the page. So let's write that down. These are my fingers, my 4 fingers. 4 fingers are pointing out of the page. So 4 fingers are pointing out of the page. My thumb's pointing down. Here's the question. What's the direction of my palm? So here's where you have to actually be a participant. All right, ready. My fingers are pointing in the direction of the magnetic field. So my fingers, take your flat hand, right hand rule, take your flat right hand, point your fingers towards your eyeball because the magnetic field is coming out of the screen towards your eyeball. The velocity is pointing down. So your thumb needs to be pointing down. The direction of my palm is in the negative X direction or this way. So I need to make really sure about that. Fingers, my 4 fingers are pointing in the direction of the magnetic field, which means they're coming out toward my eyeball, which is why I see it as a dot. My thumb is for the velocity direction. My thumb is pointing straight down. My palm is facing that way. That's the direction of my magnetic force. So I'm going to draw my magnetic force vector. This is my magnetic force vector right here. There it is. Okay, my magnetic force vector is just going to the left. And I have it. I have everything. I have my magnetic force. That's the direction my palm is aiming. I have the magnetic field, which is coming out of the screen. That's the direction of my 4 fingers. My thumb is pointing down because that's the direction of the velocity. And every time I'm doing all this, I can move my thumb, but your hand remains flat. So I am good to go. I know that this is a proton. I know it's a proton. This tells me it's a proton. F sub B is going to the left, magnetic field coming out of the screen, velocity going down. And then I'm going to say proton. Why is this a proton? Because if it was an electron, you would flip the direction. So this whole flat hand, right hand rule assumes a positive charge, If it's a negative charge, you have a choice. You either use a left-hand rule, or what I do, I just flip it. If this were an electron, it would actually move the other way. If this were an electron, it would curve. This would be the semicircle for the electron. But I don't have that. I don't have this path. I have the path that's given. So that's how I can kind of use my reasoning and my flat hand, right hand rule to say, well, based on the fact that my flat hand, right hand rule assumes a positive charge, and I'm getting this as my direction of my force direction, it's a proton. It is a proton. It is a proton, and you can see no matter where. So play this. Let's just play this game one more time when the proton is right here. When the proton is right here at this location, there's my velocity. So label that V for velocity. My magnetic field vector is still coming out of the screen. So that's my magnetic field vector. No change there. It continues to come out of the screen. And now let's find the direction of the force acting on the proton. It is a proton at this point. So I'm examining the proton when it's right here, which means, all right, fingers point in the direction of the magnetic field. Thumb, and this is where you have to be flexible. Let's do some stretching. Thumb points in the direction of the velocity. Palm points in the direction of the magnetic force. So if I'm doing this the right way, my fingers are coming out of the screen, my thumb is pointing in the direction of the velocity, and this would be the direction of my palm. My palm is actually facing in this direction, like that. That's the force, right? Perpendicular. So you can see here, this should help. This is perpendicular. Force is always perpendicular to the plane formed by the velocity and magnetic field vectors. So this is the heavy part. This is heavy lifting for sure. All right, so no matter where the proton is, F sub B always points towards center of the circle, no matter where the proton is. Regardless of proton's location. This proton could be anywhere on that semicircular path, and it's always going to be experiencing a force trying to shove it toward the center of the circle, which is right here. Here's the center of the circle right here. And so it's a centripetal force, which is why I started off with the magnetic force makes the proton move in a circle. And now you know why. So this was a very deep dive into right-hand rules and the directional relationships between all of these vectors, between F, V, and B. All right, so that was a lot. Let's just finish this. Let's actually do the problem now. All of that was just kind of set up. That was the hard part. But it's the critical part. You have to be good with your right-hand rules, and you have to, you have to remember that this is all set up for a positive charge. And what if it was a negative? Well, you would flip the result, or you would use your left hand. So there's good stuff going on, a lot of stuff going on. Number 6. Okay. F sub B equals QVB sine theta. So I'm using, again, here's the cross product version. Here's the magnitude angle version. I'm using the magnitude angle version. And you know what? This magnetic force is the centripetal force, equals mv squared over r. So this is another throwback to your prior physics course. So I'm always saying that with a lot of like drama, because maybe there's some rust. Maybe some rust has accumulated. But all I'm saying is this magnetic force is actually my centripetal force. So the magnetic force is making things move in a circle based on literally the last 15 minutes of ranting I did about flat hand, right hand rule. Okay, so number 7, well, low hanging fruit. This equals 1. This equals 1, and this is another big thing. Right? You have to be able to explain why theta equals 90. Why is the angle between the magnetic field and the velocity vectors always equal to 90? You have to agree to that or ask follow-up questions. But number 7 becomes this. Number 7 becomes QVB. I don't have to write down sine theta. Actually, number 7 becomes this, even more low-hanging fruit. QB equals mv over r. Because you can see how a velocity term here cancels with the velocity term here. So on the left side, QB equals mv over r. Not bad, except I'm not seeing my dollar sign here. All I said is, apparently this is centripetal motion. This is uniform circular motion, which you studied in your prior physics class. That's like a very core component. But that's the good news. It's for sure uniform circular motion, where the agent that is making this particle move in a circle is the magnetic force, but I'm not seeing my dollar sign. My dollar sign says, what's B? Well, I take that back. Here is my dollar sign. So I spoke to it because I didn't read it. Here is my dollar sign. So this seems to be going well. Here's number 8. B equals mv all over QR. And then now I guess here, now things were going so well, but uh-oh. I don't know V. V is unknown. I know Q. Q is the charge of a proton. And I don't know R either. So it just keeps getting, things started off so promising. I don't know V. I don't know R. I do know the mass. I do know the mass of a proton, and I know the charge of a proton. So here's what I'm going to go back to the question. And they said, well, it moves in a semicircle and it spends 114 nanoseconds in this semicircle. So number 10, I'm going to do this. V equals distance over time. Velocity is distance over time. What's the distance? It's a half circumference. So you guys remember that the circumference of a circle is 2 pi r, but this proton is not traveling through a complete circle. It's traveling through a half circle. So if C equals 2 pi r, then half a circumference equals pi r. So here's the distance, pi r. And here's the time it took. It took 114 e to the minus ninth seconds. Okay, that's my velocity term. Velocity is distance over time. Distance is half a circle. The time it's spent in half that circle is 114 nanoseconds. Let's go back. Here's number 8 again. B equals m, which I know. Maybe I put mass of a proton times V, and V is pi times R all over that 114 nanoseconds. Okay, that's my M times V all over Q, which is 1.6 times 10 to the minus 19th coulombs times R. QR, you can see the R's cancel. This R cancels with the one upstairs. So I don't know R, but the good news is I guess I don't need it. I know the mass of a proton is equal to 1.67 times 10 to the minus 27th kilograms. So now let's find B. The magnetic force, the magnetic field, the strength of the magnetic field that produces this motion. Tesla. Again, I'm going to do if because FB equals QV B sine theta. I'm just going to do a little dimensional analysis then. B equals F. So from a unit point of view, I have newtons per coulomb meters per second. Okay. And this is a Tesla. Okay. That's the answer to part A. I'll make some notes for part B. Part B says, what happens if the kinetic energy increases? If kinetic energy, so for part B, they want you to do the same thing. They want you to crank up the kinetic energy. So I'll just say this. if you increase the kinetic energy, you increase the velocity. And then this is T does not depend on velocity. All right, I just made some notes for part B because I'm assuming it might take a moment to calculate through with your numbers. So I'm going to set up the next quiz, and while I'm setting up the next quiz, review 13, 14, 15, and see if it makes sense. And in general, just look at everything on this page, because it'll take me a minute to set up quiz 3, and during that interval, revisit this stuff. Just be relentless and just be persnickety and ask yourself, is there anything here on this screen that isn't really sinking in? Because there's a lot. This is chapter 28, pretty heavy. So give me a minute to set up the next quiz, which is 34. Okay. All right, the next quiz becomes available in 2 minutes. I want to take just 2 minutes. I need to hammer home this point. Chapter 28 actually has a lot of deep dives. So as usual, we're doing a lot of the homework via class time, which is good, I think. And what we're not doing in the class, there's all of these deep dives that you have available to you. And I just want to, again, make the point I made earlier. Don't assume that there's any prioritization takes place or that any problem has any more weight versus any other problem. Don't let yourself think that, oh, the problems, you're going to focus on the problems I do during class more than the deep dive solutions or more than any other homework problem. Even those homework problems that don't have a deep dive that we didn't touch on a Tuesday class, every bit as in play as anything else. So these deep dives, to me, would be my first recommendation if you needed to use
Chapter 28, problem 46.
If you needed to use an external source. So just and there's different flavors of deep dives. Like this one is a deep dive. That's a video tutorial. And at 61, chapter 12B and Newton's second variables are known. Step 8, part B. So I just wanted to remind you guys that the deep dives, I believe, are your best bets in terms of lifelines that you should tap into beyond our Tuesday class. And to also sort of out of the other side of my mouth saying, but don't give any more weight to any one homework problem over the other. Okay, so there. So it's 10:09. You should see the next quiz problem. You should see chapter 28, quiz 3. Oh. You should see chapter 28, quiz 3. Okay. So this seems like another cross product situation. So a lot of time, I'm spending a lot of time on cross products, and that's not really intentional. It's just because, well, those other deep dives, there's a lot of other deep dives, and for whatever reason, I didn't do a whole lot of cross product solutions, or I didn't do a whole lot of deep dives that focus on cross products. So that's through no plan. That's not a premeditated, or that's not by design. So here is an electron following a helical path. Let me see if I can get a picture of that helical path. Although I did have this in the YouTube videos. Helical path. Ooh, it's pretty good. Here's a picture right here. Let's see. That is a pretty good picture. Except it's a proton, but no matter. Let me take a snapshot of this. This is showing a proton moving in a helical path. We don't have a proton here. We have an electron. So what I'll do, let me go to the textbook because I'm going to leave that as is. 1 second while I get some supporting visuals. That's another. Every picture I have is showing a proton. Well, I guess I'll just stick with it. Okay. All right. An electron follows a helical path, and you're not seeing an electron following a helical path here. You're seeing a proton. Actually, you know what I can do? You know what I'm going to do? I'm going to say everything can remain the same, but I'm going to flip the arrowheads for this to be accurate. Okay, so that's the direction. That's the direction. That's the direction. Not this. Actually, I got an even better idea. there. We're just making a little visual update. This is the if this is the direction of the magnetic field, and if this was an electron, okay, then that's accurate. And this is the helical path. So that's what a helical path looks like. It looks like a slinky. Do you know what a helical path is? It's what you get when you have something moving in a circle over and over again, but then you stretch it out. So here's an object moving in a circle. And I'm drawing it from a side view, a side perspective. It's moving around in a circle over and over again. But then if you sort of kick it towards the left, then you get this. It's still moving in a circle, but in addition to moving in a circle, it now has this horizontal component at the same time. So not award-winning, but that's what a helix is. A helix is what you get when something keeps moving in a circle, but then you give it a oomph along in a direction out of the plane of the circle. All right, so this is what's going on. What's the angle between V and B? So here goes. This is definitely cross product day. Number one, what is the angle between V and B? So here is my, okay, we can actually draw this. And if you can draw it, you need to draw it. Here's a three-dimensional coordinate system. Here's my magnetic field. My magnetic field has these coordinates. It has 16 millitesla in the I hat direction. Fine. It has negative 48 millitesla in the minus Y direction, and it has minus 28K, something like that. Okay, so this is my magnetic field. My magnetic field is, this is B sub X equals 16 I hat millitesla. This is B sub Y equals negative 48 J hat millitesla. And last but not least, this is B subscript Z equals negative 28 K hat millitesla. So if I wanted to know what does my overall magnetic field look like, it's first tail to last head. It would look exactly like this from the first tail to the last head. Let me get a different color. A different color. First tail to last head. All right. So this would be my net magnetic field. Like this. So this is my net magnetic field is just BX I hat plus BY J hat plus BZ K hat. And I have all of those unit vectors. So my electron is sitting right here. My electron is just parked, or it's not parked. My electron is moving. But at the moment my electron is right here, that red vector is the magnetic field that it encounters. At the same time, my electron has a velocity. Here's the velocity of my electron right at this particular moment. 20I. Let me change vectors. So this is a whole different scale, but here's my velocity vector at this particular moment. Ready, set, 20 I hat meters per second. Fine. Negative 26 J hat meters per second. Okay. And it's getting pretty crowded here. And then positive 55K coming out in the J hat direction. So like that. All right, this is BX I hat. This is VY J hat. This is VZ K hat. So what's my velocity vector look like? Ready, set, go. Let me get thicker. Here's my velocity vector right here. That's a little bit too thick. Okay. All right. And this is once again the velocity of the electron. V equals Vx I hat plus Vy j hat plus Vz k hat. That's the story. Here's my electron right here at this particular moment. And at this moment, this orange vector is the velocity of the electron, and the magnetic field is given by that red vector. So this is going to start spiraling. I don't know the direction that it's spiraling in because things are kind of skewed. Things are not nice and neat. I'm going off in these, these many different directions. And this is why we like cross product, because we can handle this using cross product. Good luck trying to do this like with standard, trig geometry. This is why cross product will help. All right, so here goes cross product. Number 2. Well, I know V cross B. V cross B. I can write V cross B. I can do V cross B a few different ways. V cross B is equal to VB sine theta. And here's another way to do V cross B. This would be magnitude. So I'm going to do magnitude. I can do the magnitude of V cross B that way, or I can do the old method of Saris. I, J, K, I, J. And because it's VB, this would be Vx has to come first. If it was B cross V, I'd flip it. But because it's V cross B, it's order dependent. Vy, Vc, Vx, Vy. And again, because it's V cross B, not B cross V, then comes, finally, I come with Bx, By, Bz, and then you just repeat it, Bx, By. All right, so I have these two different ways of doing cross product. And here's my dollar sign. It's saying, what is the angle between these two vectors? A says, yeah, what's the angle between red and orange? Red is B, my magnetic field. Orange is V, my velocity. So there's my dollar sign, and I think I can do this now because all right, let's just keep going. Number 3. The magnitude of V times the magnitude of B times the sine of the angle between them is IJK, IJ. And then Vx, according to my numbers, Vx is 20. So I'm just assuming meters per seconds are assumed. Vx, so I'm done with Vx. Vx is 20. Vy is next. Vy is negative 26. Negative 26. Vz, which is next in line, is for me 55 meters per second. Okay. 50, and then repeat. I is 20. J is negative 26. So 20, I'm just double checking. 20, negative 26, positive 55. And then again, 20, negative 26. B subscript X. Here's Bx, here's By, here's Bz. Bx is 16 millitesla, 16 e to the minus 3 16 e to the minus 3 Tesla. This is negative 48 e minus 3 Tesla. And my Z component is negative 28 e minus 3 Tesla, and then repeat. 16 e minus 3, negative 48 e minus 3, and I'm done. I'm just going to do a double check. This should be I'm going to do a double check. This should be 16. This should be negative 48. This should be negative 28. And they're all millitesla. So hence the E minus 3, 16 minus 48. Okay. So let's do the cross. You can do this on a calculator. You know what you should do? If you have, just for example, if you have a TI 89, whatever, you should just Google TI 89 cross product, and it will give you a YouTube video will pop up, or you'll find a link to a video or just a description that tells you how to do cross products on your TI 89. And in this case, you could use that. You could use your TI 89 to do a cross product, but I'll do it the manual way. All right, so here's this times this times this, this times this times this. All right, so you know what I get when I do the CRIS operation? Here's what I get. I'm going to get negative 26 times negative 28 E minus 3. Is that right? Yeah, I hat. And then I'm going to get my J hat. I'm going to stack things vertically, I guess. Plus 55 times 16 E minus 3. I'm leaving off units because I know what they are. 55 times 16 E minus 3 K hat. J hat, sorry. And last but not least, 20 times negative 48.3. So this would be plus 20 times negative 48 E minus 3. And those units would be K hat. And then I'm just going to double check. 26 times negative 28 E minus 3 I hat. That looks good. 55 times 16 E minus 3 J hat. That looks good. 20 times negative 48 E minus 3 K hat. Okay. And then let's flip the other way. Ready? This times this times this, and then this times this times this. Okay. So this, when I have to prepend a negative, so I'm going to go way over here just to give myself some room. I'm just going to start with a negative of negative 26 times 16 E minus 3. K hat. And then this over here, I'm going to start with a negative again, negative of 55 times negative 48 E minus 3 I hat. And then last but not least, start with the negative of 20 times negative 28 E minus 3 J hat, and then this would be plus. Okay, I'm going to do a quick double check here. All right, I should have negative of a negative 26 times 16 E minus 3. Feeling good about that. And then for my K hat, my I hat component, I should start with a negative, and then there's my 55, and then there's my negative 48 E minus 3. There's my I hat. And last but not least, here's my J hat. I should have negative, start with a negative, 20 times negative 28 E minus 3. Done. Good heavens. All right. So I'm pretty, well, I'm not, I was going to say I'm pretty much done, but there's a few more steps. I'll stick with you up to a point and then give you some nice alone time to finish this problem. But all right. So here it is. Here's my, here's V cross B. V cross B equals, and then I'm going to spend a little bit of calculator time. I'm going to cluster my I hat vectors together. Here's an I hat vector. And then here's another I hat vector. Okay, so let's do the calculator thing and just cluster all those together. What is negative 55 times negative 48 e to the minus 3 plus 26 times 28? Oh, I guess I need to first turn on my calculator. Note to students, turn on your calculator. So let me start all over. Negative 55 times negative 48 e minus 3. That's my first I hat component. And then I'm going to add my second I hat component plus a negative 26 times a negative 28 e minus 3. I'm getting this number for my I hat components. 3.368 I hat. I'm going to leave up, well, the units would be meters. The units would be velocity is meters per seconds and magnetic field is Tesla. So you could just leave it like that. All right. And I'm just going to double check this. Negative 55 times negative 48 e minus 3 plus a negative 26 times a negative 28 e minus 3. 3.368. Okay. And then just do the same thing for J and K. Let's do J. Here's J hat. There's a J hat. And then here's another J hat. All right. So the J hat's negative 20. Okay, 1.444. I'm just going to double check that. Okay, and then K hat. My K hat terms. There's two of those. Here's one of them. Here's the other one. Okay, K hat. So this is V cross B. It's a vector. It's just some vector. I have an I hat component. I have a J hat component. And I have a K hat component. So that's it. This is my resultant vector. This is my resultant vector. Actually looks like this red vector right here. This is my resultant V cross B. It's in some complicated direction, or not in a simple direction. It's not like in the XY plane or the YZ plane. It's this is the result of V cross B. All right. What's the magnitude of V cross B? Because I know what it is in terms of unit vectors. So now I need to take the magnitude because I'm focusing. This is my path I'm taking. I am saying, here's my answer. right here. That's my answer. So here's the magnitude of V cross B. The magnitude of V cross B is just going to equal the x component squared. It's going to equal the x component squared plus the y component squared plus the z component squared square root, where this is the x component right here. This is the x component of V cross B. This is the y component of V cross B. And this is the z component of V cross B. So we're just doing Pythagorean theorem to find out the magnitude of this resultant vector. So let's do that. Squared. All right, 13 and some change. 13.71296. I'm just going to double check. Yeah, except I forgot to take the square root. Okay. I better put this in my calculator memory location. Store. So definitely time to store things. And I double checked it. Let's see. Okay. All right. Done with this side of the equation. And then what's the magnitude of V? So this is where I might kind of just do some handwave or some description here. Okay. The V means the magnitude of my velocity vector. So you're going to do Pythagorean theorem again. You're just going to take Vx squared plus Vy squared plus Vz squared square root. That is the magnitude of V. What's the magnet? So I'm done with this. What's the magnitude of B? The magnitude of B, I'm writing it like this, Pythagorean theorem, Bx squared plus By squared plus Bz squared square root. I'm going to put this in calculator memory location B. I'm going to put this in calculator memory location C. And that's pretty much it. So again, I'm basing everything on this equation here, which I'll make a little copy of it. Okay, so to update this. All right, this is sitting here in memory location A. This is sitting here in memory location B. This is sitting here in memory location C times sine theta. So here's what theta is equal to. Theta equals inverse sine of alpha A all over alpha B times alpha C. And that's the answer to part A. Okay. That is the answer to part A. You know Vx, you know all of the components for your velocity and magnetic field vectors. So now the rest is just time and effort. It's 10:37. See you at 11:36, which probably gives us time for maybe one more quiz. And we won't even be completely done with this. Right now, we're just going to get the answer to A. Question, Luke?
Doesn't class end at 11:30?
Oh, that's true. I lost track. Yeah. So
You'd be giving us an hour to do this.
I will see you guys. It's now 10:38. So 10:48, 10:40, 10:49, I guess. I was looking at a different screen. It's 10:38 plus 9, 10:48, 10:40, 10:47. Back. Well, quite the heavy lift. We get the answer to part A. We actually know the angle between the velocity and magnetic field vectors, which is really saying something, considering, again, these are just shooting off into some, arbitrary three-dimensional position. So that's impressive. Part B says, does its speed change with time? So just a little sidebar commentary. And you can see, obviously, well, apparently the answer is no for B and no for C. And we would just have to explain why. So a little sidebar conversation for B and C. Thought-provoking conversation. Here's part B. Part B says or asks, does speed change with time? So does speed change? Does the electrons speed change? And the answer is no. Isn't that impressive how I got that so quickly? Does the electron speed change? The answer is no. But the question is why? This is the work kinetic energy theorem. This was a cornerstone expression from your previous physics class. The work kinetic energy theorem says that the change in kinetic energy equals work. Again, cornerstone. It has its own name. It's called the work kinetic energy theorem. There was an entire chapter dedicated to it in my previous physics class. There was an entire lab spent on it, and there was an entire exam question spent on it. This is the work kinetic energy theorem. So this is for sure a Hall of Fame entity, work kinetic energy theorem, which says, hey, the speed of an object doesn't change unless it's worked on. All right, so then here's the other takeaway. Aha. The magnetic force is always perpendicular to particle charge's velocity. And if you want to ask the question why, it's the parental response, because I said so. Or maybe more intelligently, why is the magnetic field force, why is the magnetic force always perpendicular to the velocity vector? And that's just, at this point, all I can say is this is the design of nature. This is how nature has architected our universe. The magnetic force is always perpendicular to the charge's velocity v. And again, hence the cross product. And you know what that means? That means that the magnetic force can never do work. So therefore, if that's true, which it is, why? Design of the universe. If that's true, then F sub B, the magnetic force, does no work on charge. And that's because you have to remember what work is. Work is the dot product, the product of parallels, F dx, dot product. If there's no, so if my particle is moving, if my particle is just moving in that direction, no matter the direction of the particle's velocity, the magnetic force is always going to be perpendicular. So there's never a component of the magnetic force that's in the same direction as the particle's velocity. No work means no change in kinetic energy. No change in kinetic energy means no change in velocity. So that's why that's a no for part B. Part C says, does theta ever change with time? And I guess I would look over here, right here. Here's sine theta. Sine theta depends on these. It depends on the magnitude of V. None of these change. None of these change as a function of time. So V is always a constant because it never changes. B, that's just my external magnetic field, which is just imposed upon me. Everything here is a constant. V cross B is a constant. No change in time. And then D says, what's the radius of the helical path? So back to an equation. All right, so I better start numbering things. That was just me sort of hand waving and talking through part B and part C. Part D says, what's the radius of the helical path? So I'll pick up here. Part D. Part D. What's R? R of that radial path is the $sign. And remember, how do you get a radius? You take this charged object right here is just moving around and around in a circle over and over again. But then you give it a nudge in this direction. And next thing you know, you get that slinky helical path. Okay, so we actually had an expression for this in this quiz, I think. There it is. It's right here. Here's the radius of the helical path. You know what? Well, okay. I'll fast track this a little bit. So number 2, it's moving in a circle. If it's moving in a circle, the magnetic force is the centripetal force. That's if it's moving in a circle, which it is. And you could say, well, it's not moving in a circle. It's moving in a helix. But again, we're only going to look at the circular motion part of this. We're not going to care that it's moving along X according to this. We're not going to care that it's moving through some length. We're just going to look at the circular motion part. So Q V B sine theta, and I do know theta now, equals mv squared over r. So this is centripetal motion. This is F sub B. And this is my centripetal force. And the centripetal force is in play. The centripetal force is present because it's moving in a circle. Okay. So, okay. V's cancel, some low-hanging fruit. This V cancels with one of those V's. Let's solve for R. Let's isolate R. Number 3, R equals mv all over QB sine theta. All right. And good thing we have a lot of this stuff in calculator memory location. And in fact, I better put my theta, store alpha D. I better put this in memory location D. All right. So number 4, the radius of this circle. Yeah. The radius of this circle is R equals, and is this is an electron. Here's the mass of an electron. Ready, set, go. 9.11 times 10 to the minus 31st kilograms That's the mass of my electron. Here's the velocity of this electron. It's sitting in memory location B. All over Q, the charge of an electron is 1.6 times 10 to the minus 19th coulombs. The magnitude of B, the magnetic field, is sitting there in calculator memory location C, times the sine of my theta, which is sitting there in memory location D. All right. All right. I guess they want the answer in nanometers. Are okay. Concludes this problem. Let's do one more. I'll get it ready. Chapter 28, quiz 4 is problem 45. Huh, okay. Problem 45. Okay. Last quiz, chapter 28, quiz 4. Okay. Chapter 28, quiz 4. A wire. A wire is carrying current. All right. So again, 3 dimensions. That's cross product or stuff. Three-dimensionality is a big deal in chapter 28. Stuff is for sure happening in X, Y, and Z, which is why drawing everything is turns out to be a big component. It's not just like a little checkbox item. It actually becomes very important, at least for me. Well, for me as a student and me as an instructor, because I need to see the visuals to make sure you understand all of this 3-dimensional stuff. I have a wire carrying a current in the positive X direction. So there's my coordinate system. I'm going to draw a wire. Here is a here is a wire. Okay, there's a wire carrying current in the positive direction of an X-axis. So that's satisfying the criteria. wait for it, I think. Try that again. Wire. Okay. So this is carrying some current. So I stands for current. And just by way of backtracking, I is charge per time. And it's given to me as 0.740 amperes. And an ampere is, I could just say the same, 0.740 coulombs per second. So just taking an opportunity to backtrack a little bit here. All right, here's the positive X direction. This is positive X direction. That's the direction of the current. Okay. And now I have a magnetic field. So I got to draw the magnetic field. My X component is 0. My Y component is that number. So here's my magnetic field. That's B subscript Y. And then here's my Z component is coming out of the screen, which is quite a bit larger. Okay. So this is my Y component. This is B subscript Y equals 3.7 E minus 1, 2, 3, 4, E minus 4 Tesla. This is B subscript Z given as 8E minus 3, 8E minus 3 Tesla. I don't have a Z, I'm sorry, I don't have an X component. So here's my net magnetic field. Looks just like this. So this is B. B equals BXI hat, which is 0, plus BYJ hat, plus BZK hat. All right. Here's my velocity vector. Here's my what's the direction of my charge flow? My charge, it turns out I have a bunch of charges, but let's just look at one charge. Whatever charge I look at, this is the direction. This is their direction, that purple vector. So that's V. All right. And then the question is, what's the force acting on this wire? So and again, this is a 25-cent version of your $100 YouTube green sheet lecture video that derives the expression we're going to use. This was empirical, meaning this equation that I'm drawing right here is just what people observe nature doing, QV cross B. This was not derived. It's just saying, hey, let's just do a whole bunch of tests and let's consolidate all of our findings from all of these tests. And it turns out this is what we get. And this is how nature is designed. And you know what? I'm going to do this just because we're doing good on time. This won't take a lot of time. But remember, the F sub B vector is always perpendicular to V and B and the plane formed by V and B. So I'm writing this down like maybe a second time or a third time for a reason, because it's sort of basic. It's important, by V and B vectors. Okay. There. I'm going to go to, well, I guess I'm not going to go. It's unit vector time. All right. So here, well, I will go to just magnitudes. All right. So magnitudes is magnetic force equals QV B sine theta, where once again, just as a sidebar, theta is referring always to the angles between those two vectors. And now what I'm going to do is keep going with this and saying, well, okay, the magnetic force is Q. Velocity is distance over time. So here's distance. It's whatever the length of that wire is. Here's time. There it is. And then B sine theta. All right. So the only substitution I made is I said, what's the velocity of a particle? Well, it's whatever distance divided by time is. And this is the length of the wire, which for me, the length of my wire is given 40.9 centimeters. So now watch how I go from step 3 to step 4. The magnetic force acting on this wire, not the charge, but a wire, because a wire carries a bunch of charges, is Q all over T times L B sine theta. I just kind of clustered these together. Here's Q and here's T. Q divided by T. Q divided by T is known as current. So number 5 is the force acting on this wire. And this is at the heart of motors. Why do motors work? Because there's a magnetic force acting on those wires that are carrying a current, equals I L B sine theta. And if you remember, this is the exact same form as cross product, equals I L cross B. These are equivalent. ILB sine theta captures the perpendicular product. So does this. Okay. So again, that's the 25-cent tour of the YouTube lecture videos. Let's figure this out. All right. So ready. The magnetic force acting on this wire, and this wire is just carrying a whole bunch of charges, equals I, and then I hat, J hat, K hat, I hat, and you could use your calculator on this, J hat. All right, so it's I, which is just some scalar that's sitting out there, kind of isolated. And this would be Lx. So I'll do it like this, Lx, Ly, Lz, and then repeat Lx, Ly. And because it's L cross B, it's L comes first, and then B follows, Bx, By, Bz, and then repeat Bx, By. Now, one more time, but with feeling. One more time, but with numbers. So I'll just take a snip of this. Well, I don't know why my snips never work all that well, but here's the, with numbers, number 7. Here's the force acting on this wire. Why do we like the magnetic force? Because forces do work for us. And in this case, this magnetic force is going to do some work on this wire. It's going to be applying a force. And maybe that wire is movable. So if there's a force that acts on this wire, it's going to move. And the next thing you know, you have the seat adjustment control on your front driver's seat moving forward or backward. And that's because it's a motor. So I times the current times I hat, J hat, K hat, I hat, J hat, Lx. What is L sub x? What does the L vector even mean? It means, I guess, sidebar conversation. L, this length vector, this is the length vector. Length vector. Because it's a vector, it has a magnitude and direction. The magnitude of this length vector is the wire length in this case. The direction, I'll say theta. Theta is the same as current direction. So that's how I can call that. That's what I'm using for my length vector, same as current direction. And I know the direction of the current. It says the current is going in the positive x-axis direction. So I do know L sub x. L sub x is 40.9 centimeters in the positive X direction. So this would be 40.9 centimeters. My numbers say 40 point, well, I better go to meters, 0.409. 0.409 meters in the X. Yep. Just double checking. And it's purely in the X direction, which means 0 for J, 0 for K, and then repeat 409. And B sub X, for me, B sub X is 0. This is 0. B sub Y is given as 3.7 E minus 4. 3.7 E minus 4 Tesla. B subscript Z, the K hat component is 8E minus 2, no, 3, 8E minus 3 Tesla. 8E minus 3, and then repeat 0. 3.7 E minus 4, and then crisscross. Here goes. Ready? What is I times 0 times that? That equals 0. What is J hat times 0 times 0? Well, that's equal to 0. What is K hat times 409 times that number? Well, that I'm just going to put that, well, I'll do that right now. 0.409 times 3.7 E minus 4. Pretty, well, not super nasty, but store alpha A. All right, well, I do get a number of 1.5133 E minus 4 K hat. And I'm going to double check that. 0.409 times 3.7 E minus 4, 1.5133. Okay. What about the cross operation? Ready? I've got to come back this way. K hat times 0 is equal to 0. I hat times 0 times something is that's 0. Then I have J hat times this number. That's not equal to 0. So it's going to be, I got to start off with a negative, like it or not, negative 0.409 times 8E minus 3. And that's my J hat component. So that's my result of L cross B. And then I got to take this entire result, and multiply it by I. Take that result and multiply it by I, which for me, my current was 0.74 amperes. And that's the magnetic force. All right. That's the magnetic force acting on this current carrying wire. So, okay. Negative 0.409. Okay. Done with our last quiz. All right. Well, I can't think of any other reminders or nudges or tips or advice, because I covered it mostly at the beginning of this class, but good to go. See you guys Thursday. Let me know if you have any questions about this. If you don't have any remaining questions or comments or requests, then you can drop off and I'll see you all Thursday early. And I'll leave this screen up for a bit in case you're still referring to it. All right, you
Can you
guys.
reopen quiz 3 later tonight?
Yeah. Quiz 3.
Yeah, thank you.
Okay. Yep.